Welcome everyone. Today we'll be talking about sniffing with multiple probes, why it's a good idea and how to do it. I'm going to start by introducing the speakers. Today's speakers include our CTO, Lee Chenitz, who's had a lot of wireless experience in Wi-Fi and other technologies, such as UMTS, CDMA. He's had a lot of work exposure at the standards organizations, at the Wi-Fi Alliance and IEEE and TIA and ITU, and he's worked closely with the FCC. Lee holds 20 patents. Paul Darcy is our principal engineer, and he's been in the telecommunications industry since 1990, primarily in the 3G, 4G, 5G, LTE area. And he has had his hands in silicon design. And Paul holds 19 patents. Rada Kanan is our systems engineer, based in Dallas, the Dallas area in Texas. She is one of our experts on how to operate the test bed and how to automate tests. So she's going to help us with some demos today. And with that, again, I keep forgetting, the rules of engagement are, we do welcome your questions. You can submit them either in the Q&A, click the Q&A button on the bottom of the screen, or you can raise your hand or simply post a chat and we'll try to get your questions. Please be patient with us. We're going to take breaks to answer questions, so we may wait until the end of a slide or two. Okay, so with that, if you do have, if you're new to Zoom and have questions on how to do all that, just post us a note, and we'll help you out. With that, we'll get started.
All right, Fanny, thank you very much. All right, everyone. Hi, and welcome to our fourth in our action-packed seminar series on how to test wireless devices and how to perform those tests in an octoScope wireless personal test bed. In previous sessions, we've discussed things like testing in the presence of multipath, the use of turntables for testing in order to promote repeatability and reproducibility. And we did an introduction to OFDMA and Wi-Fi 6 test methods. Today we're going to focus on a critical piece of the testing process, packet sniffing. And we will discuss it in the context of something we call the synchrosniffer. So as you can see from the agenda, we'll start by explaining what the synchrosniffer is, what do we mean by that, and then talk about, sort of try and motivate synchrosniffing in terms of its usefulness when we're testing in complex wireless topologies, also when we're doing OFDMA testing. So a bit of a tie together with the last seminar we did, the third one. We'd like to do live demos during these seminars so that you can see what we're talking about. We will do a couple of demos. We'll show you the live synchrosniffing of OFDMA traffic and also live synchrosniffing of a roaming event. And this will make more sense as we get into this conversation, but when you're doing sniffing the way we're talking about it using a synchrosniffer, you do get a lot of information and it can be fairly complicated. So we will talk a little bit about steps we're taking to simplify that complex information, some of our visualization techniques. Okay. So octoScope test beds, or what we call the octoBox, these test beds have a lot of advantages, and especially those of you who are either familiar with our products or have attended some of the previous sessions will have heard us talk about many things. One is that they're small and compact. So here's a picture of one. You can see it's roughly the size of a large microwave oven. They're completely isolated, so the test environment is completely separated from any of the external environment that could cause noise and interference and change the test results. And for multiple reasons, those as well as others, these test beds allow you to dramatically reduce the time it takes to do a test. So tests that might take days or weeks can take only hours to do in a test bed like these. But there's another advantage that maybe doesn't get emphasized quite as much, but we want to emphasize it today. And that is that in a test bed like ours, like the octoScope test bed, you can actually test some very complicated wireless topologies. And these are topologies that are very hard to test in other chamber-like environments. And when I'm talking about a complex topology, I'm talking about things that are of a lot of interest to people these days, like wireless networks that are constructed as a mesh, that use extenders, or repeaters, or something like that. I've got a picture here from the Wi-Fi Alliance talking about their Easy Mesh certification. So there's a lot of focus in the industry. Certainly our experience from our customer base is that everybody's very interested in testing these topologies. And it turns out that a test bed like ours makes that a lot easier to do than for example, large chamber. So why is that? If you try and use a large chamber to test a complicated topology like we're talking about, imagine a mesh. The problem that you have is that in a big room like the one shown here, if you put a bunch of devices in there, say a mesh, or say a root access point, and then a few mesh access points, and then a station that you'd like to roam across those devices, the problem is that all the devices are going to hear each other, and the station device will have very little incentive to move from one to the other. The reason for that is shown by the path loss curve that's on the bottom of this slide. You can see what we've plotted here is path loss as a function of distance. The distance is in centimeters, and you can see that in order to get up to something like 60 dB of path loss over the air, you need to be out nearly 5 meters in free space, and these kinds of environments are basically free space path loss model. And the issue with using some kind of environment like that to do a roaming test then is that 60 dB of path loss is not a lot. It's not enough really to break a wireless link. So if you move a station away from an access point, you've only got 60 dB of path loss. As far as that station's concerned, it's still pretty close to the root access point, and we'll have a pretty hard time moving from there to, say, a mesh access point. The nice thing then about a multi-chamber test bed of the kind that we use at octoScope is that we put all of the devices, so for example, the root access point and mesh access points, into separate isolated chambers, and we connect them together via programmable attenuators. So because of that, we can create fully connected meshes, for example, like the one shown here. And the attenuators give us full control over the distances, which lets us create pretty much any topology we'd like to create. So we can essentially move the root access point and the mesh access point as close to each other or as far from each other as we want. And the station, which is shown in the bottom here, and you can see the station has a connection to each of those access points, can essentially be moved in attenuation space, although we never have to move anything physically, can be moved in attenuation space close to the root, far from the root, close to either mesh. And so just via software, we can do a lot of different topology changes and a lot of different roaming kinds of tests in a very simple way. And again, a way that's really difficult to do if you just have a single large chamber. So the test bed that we have been using for these seminars and that we'll use again today is a test bed that we call the Stack Max. We call it that because it's essentially the sort of maximal test bed that encompasses most of the tests that we see our customers wanting to do. So it's made up, as you can see here, if you look at the picture on the left with the open doors, of 5 different isolated chambers, and 3 of them make up a full mesh, just like the picture I just showed. And one of them can contain a station that can be roamed across that mesh. So exactly like the picture I just showed, this one, except configured somewhat differently. And when we show the configurations, we tend to draw it this way. So here what we've got is a 3-node mesh, which is in the middle, these 3 boxes. And you can see via these red lines, these are the backhaul links that essentially connect those boxes together. And there are programmable attenuators on each line. That's what lets us change the topology at will. And then on the left-hand side, we have the box that contains the station, either a third-party kind of off-the-shelf station, like a standard phone, or one of our test instruments, which we label here as StayPal. And you can see via the other sort of slightly thinner red lines that there's a connection from this box to each one of these boxes in the mesh. And that's what lets us do roaming or band steering or whatever else we'd like to do. So we can create these devices, these topologies, and modify them at will. So let's get back to the topic of sniffing, which was kind of the point here. So once we have a complicated topology like this, sniffing is now no longer kind of a simple matter, right? It's not possible now to just say, well, I'm just going to put a sniffer in here and sniff what's happening. We have multiple isolated chambers, and devices are kind of connected to one, connected to another. It's changing during the test. So there's multiple locations. There's where the client device lives, and there are the various elements of the mesh. And it's very, very possible to have multiple bands that you need to sniff on, especially if you're doing band steering on tests, band steering tests on a single device, or even roaming across devices and across bands at the same time. By the way, this last one is a demo that we're going to do live near the end of the seminar, roaming across devices and different bands. So just to give you a sense of what I'm talking about here, here's the same picture we had before, and let's kind of walk through what I'm saying. Imagine a case where we have a handset that we like to roam across this mesh. So initially, the station's connected via this RF link to the AP in this top box. Obviously, the station doesn't actually move. The station remains in the isolated box over here on the left, but I'm moving it around to give a sense of what the roam looks like. And via changing of attenuations, we can have it roam down, for example, to this box, which is in the middle. We may be interested in sniffing what's going on when it's connected to the first, say, root access point. We may be interested in sniffing what's going on when it's connected to, say, the mesh access point. Depending on how the mesh is configured, there may be communication going on between, for example, the root access point and the mesh access point. So it may be interesting to sniff that traffic as well. So we have sniffing all going on all over here. And who knows, it may well be that this took place on different bands, maybe starting on one band, roaming to another band. The backhaul could be on a completely different band. So we may need to sniff that as well. So there's a lot of different locations and potential bands that we need to sniff on. So the question then becomes, how can we get at all of that information? And that's where we get to what we call the synchrosniffer. So this is something that's more than just a regular sniffer. The synchrosniffer, what we mean by that is a test bed with the ability to have multiple sniffers placed at different locations in the test bed, sniffing again different traffic in different locations, coming from different devices and even on different bands. What we mean by synchro is that all of the sniffing devices are time synchronized. And we do that in our test bed using IEEE 1588, or Precision Time Protocol as it's known, to synchronize all of the sniffing devices together so that when we gather packet capture information from each of them, we can combine that packet capture information into a single combined file where the packets are shown with synchronized timestamps. So you can actually see what's happening on different devices, maybe in different bands, whatever it might be, by following through that packet capture, and you can actually see what's happening in a synchronized way. It turns out that this is really essential in order to be able to look at sniffing captures when you're doing complicated roaming scenarios, and as we'll discuss in a little bit, also if you want to look at traffic in an OFDMA link. One thing you may be wondering is, so how well synchronized can a set of sniffers like that be? Again, we do use IEEE 1588 to do this. That standard lets you synchronize devices extremely well. It depends a lot on the quality of your clocks and things like that. But in our own testbed, we have looked at the synchronization, and one way we can do this is by setting up sniffers. We set up 4 sniffers, for example, to look at the same access point, and we're just watching the access point's beacons. And then we can analyze that capture and find the beacons from in each sniffer that are the same. We can do that by looking at things like the sequence number of the packet and things like that. And as you can see in this plot, so this is just a bar chart of how many sniffers captured each packet. You can see that the vast majority of the time we see those beacons in all 4 of the sniffers. Occasionally we see it in only 3, but again, mostly 4. One of the nice things also about having a set of synchronized sniffers in a testbed is that sniffers are imperfect devices. They are going to miss packets every now and then. And if you do have multiple sniffers, you dramatically decrease the probability of missing a packet, because even if you don't get it in one sniffer, you're highly likely to get it in another. So when we have that data, we can then look at the timestamps from all of the different pairs of captures that are the same beacon, and plot those timestamps. And if you look, that's what this data is showing down here. The standard deviation of that is about 50 microseconds. We continue to work on narrowing that as much as we can. But one of the ways we can do that actually is to use the fact that we can identify the same packet in multiple traces, and then we understand the offset in time between the sniffers, and we can use again sort of packet matching to increase our synchronization accuracy. So when we talk about a synchrosniffer then in our testbed, what we're talking about are, again, multiple sniffers, all tied together, synchronized using PTP, and simultaneously capturing. Those sniffers can actually be in kind of multiple different configurations. We can have what we call monitor mode probes, or what are known in the industry as monitor mode probes. These are this is a sniffer that's essentially capturing all of the traffic in the air, but it's not part of a link, of a traffic link. We also have, our devices, our test devices can also function as traffic pair endpoints, either access points or stations, and they can be sniffers while they're participating in the traffic pair. So we call that inline sniffing probes, and that can happen either when the device is in access point mode or in station mode. So there's multiple different kinds of synchrosniffer probes we can have, again, monitor mode probes or inline probes that are either access points or stations. But they all get tied together, and the data all gets pulled back and then merged into a single PCAP file for final analysis. So what that merged PCAP file looks like is shown here. We're actually going to show this live as well a little bit later. But just so you understand what you're looking at here, you're seeing what looks like a regular PCAP file in Wireshark. But what we've done is when we capture our packets, we actually stamp each packet with information about the name of the sniffing probe that captured the packet. And then we are actually merging the individual packet captures from the different synchrosniffer probes together into this common file. And so you can see here that if you just scroll down, you can see that we have packets here all captured by sniffer 2. And then we begin to see packets also from sniffer 1. Sniffer 1 and sniffer 2 sort of alternating. And then now we're seeing a lot of packets being captured by sniffer 1. This is actually a fairly common signature for a roaming event. Looks like the device was first near one access point, which is being sniffed by sniffer 2. Then it moved to another one, which is being sniffed by sniffer 1. You will actually see exactly this happening when we do our roaming demo later in the seminar. So you'll see this happening live in what's actually really a really nice demo of this functionality. So I wanted to motivate the idea of a synchrosniffer using this rationale of complex wireless topologies for 2 reasons. One, it is an excellent description of why you need a synchrosniffer kind of model, and the other is that that's actually how we first developed the synchrosniffer. It was exactly for that reason, for being able to sniff at multiple points in a complex topological deployment for wireless devices. It just so happens, though, that as the Wi-Fi 6 has become the primary technology of interest in the Wi-Fi industry, everybody's talking about it, everybody's looking at how it works. People are still developing on it. It's turned out, what we kind of discovered is that the synchrosniffer turns out to be vital there as well. So, again, what we're saying here, right, is that synchrosniffer, great for multiple locations. I just described that, but also incredibly useful for OFDMA. And it's possible that when I try and convince you of that, you might be saying, well, why, right? I mean, if all you're doing there is listening to multiple devices, can I just take a monitor mode sniffer and turn it on and hear the traffic from all the devices? That's what I usually do, right? In anything up to Wi-Fi 6, that's what I would do. Just put a sniffer in place and sniff everything. So the answer to why this is true is that, with OFDMA, it's just more complicated than you think it is. So let me explain a little bit why. OFDMA is a multi-station technology, right? I mean, that's basically its point. So this is operating in both the uplink and downlink directions. So let's talk downlink for a second. When an access point is sending packets to multiple stations simultaneously, the information all goes at the same time, and it all goes in one big packet, one bit packet sent from the access point to these stations. The way that the stations can tell, which information is for them is that the information in that packet has been broken up into different, what are known as resource units. That's basically pieces of the channel. So that's what I'm showing in this picture. I've got an access point up top. I'm talking to 4 stations on the bottom. The access point has already told the stations that, for example, station 1 is getting this part of the spectrum labeled 106. Station 2 is getting this part of the spectrum labeled 52, and 3 and 4 are getting these 2 chunks labeled 26. So when the packet flows down, it comes from the access point to the stations like that. The whole thing works as well in the other direction. It looks something like this. The access point will have told the stations what spectrum they can use, what parts of the channel they can use to send their information. Now they're going to send their information at the same time. This is not one big packet. These are separate packets, one from each station, but they are coming in different parts of the channel. Again, using different RUs. Notice that the channel is broken up differently from what I showed in the downlink direction, and that's because that's the way things are. There's no reason that the downlink use of the radio channel, so the breaking it up into resource units, needs to be the same as in the uplink direction. In fact, it's quite often not the case. So in this case, I've got 4 packets all flowing through the channel that way and arriving at the AP all at the same time. For, by the way, more details on OFDMA in general and all that kind of stuff, if anybody on here did not catch it, we did discuss this in some detail in our last seminar. So the link is here, also at the end of the presentation. So these are what are known as multi-user packets, right? And the packets from the AP down to the stations are known as HEMU frames, and the packets from the stations back up to the AP are what are known as HE trig frames. And the tricky thing, right, is that a regular sniffer can't see them. So those packets, those HEMU frames and those HE trig frames, aren't visible to a standard kind of regular sniffer, regular monitor mode sniffer. Let me show you what I mean by that. So here's a sniffer trace of some OFDMA traffic where the sniffer is just a kind of a vanilla regular sniffer. So what can I see? I can see here what's known as a trigger frame. So this trigger frame is indicating to the stations that they should send uplink traffic. So we're mostly going to be describing uplink traffic, although pretty much everything I'm saying here works in the downlink direction as well. So this trigger frame indicates that there should be uplink traffic coming. The next thing I see is a multi-station block ACK. If you look down here, you can actually see that that block ACK is ACKing packets from 5 different users. They're listed here. So I had the AP telling the stations to send. Then I have the AP ACKing the data. But the question is, where's the data packets, right? I don't see them. And that's really, I'm just showing you what I just described in the previous slides. The packets, unfortunately, are not visible to this sniffer. But if you have a proper kind of OFDMA capable sniffer, then things look different. Here's the same thing. I have a trigger. I have a multi-station block ACK. You can look down. Well, actually, I don't have it, but you do have a multi-station block ACK here. And if you look in the middle, now you can actually see data frames. And if you look right here, I've highlighted one of those data frames. You can see that the frame format is that HE trig format. So those are the packets that are coming from the station back up to the AP in response to a trigger frame. These are multi-user OFDMA packets. So that's great, but now here's the next problem. As I said, with OFDMA, everything's complicated. So an OFDMA sniffer like this one that lets us see those HE trig packets has one important limitation. And its limitation is that it can only watch the multi-user traffic to and from one OFDMA station at a time. So if I actually have something like an AP talking to 4 clients, and I would like to see all 4 of the data packets, or that is the data packets from all 4 of those guys, I'm going to need more than one sniffer, because each sniffer can only watch one guy. So that's where the synchrosniffer comes back in. Again, it was exciting to us when we realized that we already had the tool necessary to be able to look at that kind of OFDMA traffic. So here's our stack max again. You'll remember the stuff on the left was what we used for roaming. The stuff on the right now, highlighted in red, that's our primary OFDMA testing configuration. Again, I won't go into great detail. We did a lot of detail last week, in the last seminar. But what I'm showing here essentially is an access point shown in this center top box. And then on the right-hand side, I've got what are known as our stay pals. These are our PAL testing devices that are OFDMA capable stations, and there are many of them in that box. There's actually 16. And therefore, we can set up 16 stations for OFDMA, so you might have the AP talking to 16 stations, or you can use that for synchrosniffing. And that's where it gets kind of interesting. So the state pals in that PAL box can be configured in pairs. So you don't have to think of them as just individual separate stations. You can think of them as pairs where you have one sniffer assigned to each traffic endpoint. So we're showing the 16 state pals in that box and how they're connected in to talk to the device under test. So again, we have 16 endpoints. Up to 12 of them can be set as synchroSniffer probes. Those are the brown ones that are shown in this picture. So that means that we can watch, if we want to, all of the OFDMA traffic using multiple OFDMA capable sniffers. So we can actually assign, for example, one of the state pals to be a traffic endpoint and another sniffer to be a monitor, and to monitor that particular endpoint. So for example, these two can be a pair, an endpoint and a sniffer, and then these two can be a pair, an endpoint and a sniffer. We can do that throughout the whole thing. So we can end up, for example, there are many different possibilities, but we could end up with 8 traffic endpoints and then 8 sniffers that are watching, each sniffer watching one of those traffic pairs. So the real kind of killer combination from an OFDMA sniffing point of view is synchrosniffing with OFDMA capable sniffers. So in that case, as you can see here, what you'll be looking at are packets that are being captured, for example, by one of our state pals that I've labeled here as state pal 2, other packets that are being captured by, for example, state pal 3. And they're all HE trig packets, and they're all being time aligned via the synchronization of the sniffers. So, so that's where we get into some, kind of really interesting and powerful capabilities from an OFDMA point of view. So with that, and I'm not hearing that there's questions yet, I'm going to turn this over to Paul, who's going to walk us through an example, actually, of synchrosniffing OFDMA packets from multiple stations.
Okay, thanks, Lee. Can you see my screen? Nope.
Not yet. Still seeing. There we go. It's coming now. There we go. Yep.
So to expand on Lee's comments on the use of synchroSniffers and to capture OFDMA traffic, we've set up a reduced test configuration here where we have 4 endpoints, traffic endpoints, and 4 synchroSniffers. Initially, the sniffers are basically set up to sniff on AID 0. So we're going to be seeing, the general packets. So here you can see that the system is up. Start a capture. And basically you're seeing the capture in progress. One thing, as pointed out by Lee, when I actually tried to check on basically HE trig frames, there are none available. When I can turn around and essentially allocate a specific aid to a specific sniffer,
Right, so what Paul is doing here is pointing the sniffer at a specific station now.
again, you see basically that suddenly HE trig frames start appearing. information. Here you can see basically HE trick frames. Similarly, as I continue to add to add sniffer capability to individual endpoints, now you're seeing probe 2 come in, probe 3.
And those packets again are showing up in a single PCAP file and time aligned because of the synchronization.
Yeah. And we can keep on doing it. You know, obviously we have the 4 sniffers. I think at this point, in fact, the capture is terminated, but I think people can get the point that as long as we can assign a single sniffer to a traffic endpoint, we can actually capture both data and control packets.
Yep. Okay. Yep. Thanks, Paul. So right. So that is, that's basically kind of showing live what we were talking about there, which is that we can assign specific AIDs to specific sniffers, and then each one of those sniffers will be essentially shadowing one of our traffic pairs. And then using the synchronization, we can pull all of that together into a single combined file. I think one of the things I actually wanted to mention was you saw the way Paul assigned the AIDs to the sniffers. That's using some sort of prototype functionality that we have. All of this functionality is being pulled into our main software package, and some of it will be quite automatic in terms of the assignment of AIDs to sniffers, and others will be under user control. But what you saw there was the functionality being demonstrated.
We have a question from Bruce.
Yeah.
Why can't the monitor mode station see all RUs in an OFDMA transmission? Can't it see the whole channel?
Yeah, so the reason is that the sniffers tend to be, act like stations devices, and there just are no, so the information that is required in order to know how to break up the channel is encoded in a couple places. If it's downlink, it's in what's known as the SIGB header, which the station would then have to decode. And then what stations do is they decode that, and then they pull out the part that's for them. In the other direction, we'd actually have to grab a trigger and then decode the information for essentially all of the users. There's simply no devices that do that. Devices, were not created to operate that way. So access points can do that in one direction, in the uplink direction. And we mentioned before that that our PALS devices working in access point mode, as well as in station mode, but in access point mode, can also be what are known as inline sniffers. So a PAL6 as an inline sniffer can actually see all of the traffic from all of the AIDs and all of the RUs coming to it. But that's kind of the only device that can do it, and it can only do it for uplink traffic. So if you really want to be able to see uplink or downlink traffic or something like that, the synchrosniffer is really currently the only way to do that. Okay. All right. So hopefully you get a sense then of how much data you can end up gathering. OFDMA again is a multi-user technology. I mean, that's where it really it's focused on. And so almost by definition, you're going to be getting a lot of statistics. You'll get a full set of statistics that you would get really kind of from any traffic situation. And then there's additional statistics that you're going to get related to OFDMA, things like RU allocation and other information. So if you try and look at all that information in, kind of together into 2D plots, it can be sort of overwhelming. This, for example, shows the kind of data that we're already extracting from a link when we have even just a non-OFDMA station, right? We're looking at things like signal strength and data rate and MCS and streams and bandwidth congestion. If you look on the left, there's all kinds of other statistics, things like, jitter and packet loss and things like retries. There's just a ton of information that's available. Now, if you need to expand that to say like, well, I don't just have one device in this link, I have multiple devices in this link, and I want to look at that kind of information, but as a function of AID, for example, or RU, or whatever it might be, you can imagine that it's difficult. It can be difficult to understand how you would visualize that. So we have actually been working on ways to get at that problem. And would like to demo a little bit of that thinking here today. I'm going to show this as a live demo in just a second, but just before I do that, let me give you a sense of what's going on here. As you saw, we capture packets using our sniffers, each one tuned to a separate AID, and we merge all that together using the synchrosniffer. So when we're done, we have this fairly complicated and dense PCAP file. And the question is, can we come up with a good way of giving a sense of what's happening in there? So what we're showing here, so each of these colored blocks represents a packet, one of the packets that's in there. The colors, as you can see here on the left, represent the AIDs. So the AIDs are color-coded. The axis over here on the right-hand side is the time axis. So that shows us when the packet arrived in time relative to the first packet in the capture, and the width of it along that axis represents the packet duration. On the vertical axis, we're showing the MCS of the packet, and that could be anything, actually. It doesn't have to be MCS. We can do that for number of streams or signal strength or whatever we'd like. And then on the axis that's kind of in the front here, we're calling that bandwidth. So what that's helping us see is essentially what RU that packet either was sent or received in. So, in either the uplink or downlink direction. So, so this is a way we can kind of visualize this fairly complicated set of data. And let me show you what that looks like in kind of a real-time view. So here's a view of that data. This is very similar to the data that Paul just captured for us live. What we're seeing here is the first set of packets. So you can see that there are packets from 3 different AIDs, AIDs 1, 2, and 3. You see how they're color-coded here, the blue and the red and the green. If you hover over them, you get information about each packet. So for example, you can see that AID 2 here was captured by our probe. You can see the probe ID. It was captured by probe state pal number 3, whereas AID 3 there, the blue one, he was captured by our probe number 7, and then the green guy was captured by our probe number 6. And you get a lot of other information. You can see the MCSs and where it showed up in the band, things like that. We can actually kind of spin this around and look at it in a couple different views. So if we look at it this way, you can get a sense of the packet kind of as it arrived, when it arrived in time, how long it was, and what part of the band it arrived in. So you can see that each one of them got a 20 megahertz RU allocation. And if we look at the I guess if we go back to the, well, we can look at it in this orientation as well. You can see, again, the different RU allocations, and now you can also see that 2 of the packets showed up at MCS 11 and 1 of these packets showed up at MCS 7. So, kind of have this way of trying to make the information a little bit more understandable, a little bit more visible, and we can essentially walk through the capture then this way if we'd like to. So here we've zoomed out just a bit, and we're looking at a number of packets at a time. You can see how, for example, AID3 is primarily getting assigned the 20 megahertz allocation over there in the left. Although you can see that it jumps around as well. There's an AID3 allocation that was in somewhere else. You can see how sometimes the packets are getting 20 megahertz allocations, or the users are. Sometimes they're getting much longer allocations. You can see one here with an AID4 that looks like it's getting a full 80 megahertz allocation, where's that? Yeah, basically all the way through. As we scroll through, you can again get an understanding of how the stations are being allowed to use the spectrum, and how the AP is using the spectrum to communicate with the stations. Okay, if there's no questions on that, again, if you do have questions, we'll come back, we'll talk about it some more. But so that being said, if you remember the way that we kind of motivated the whole topic of synchrosniffing at the beginning was based on this idea of more complicated wireless scenarios with roaming and meshes and things like that. So what I'd like to do now is have Radha walk us through a demo of synchrosniffing while a station is roaming between 2 access points, 1 access point on the 2.4 gig band and 1 on the 5 gig band. So you'll see it roaming not only between devices but across bands, and you'll see how the synchrosniffer can let you follow that in real time.
Meanwhile, we have a question, Lee, if you want to take it.
Yeah, sure.
From Bruce. Have you seen how various traffic types impact our RU allocation? How do clients report their data requirements?
Oh, that's a pretty interesting question. So not exactly the topic for today, but yes, we definitely do see that. That different traffic types will seem to impact the RU allocations. Just by the way, we are focused right now a lot on trying to figure out how to make the information visible. We haven't focused so much on really, say, like diving into the details of what the schedulers look like or what they're doing or if they're doing things well. But we definitely see certain traffic patterns where an AP may be allocating, for example, let's imagine one where we have 4 stations, and we'll see RU allocations that will be on an 80 megahertz channel 40 and 40, and then 40 and 40 maybe for a different pair, but always 40 and 40. And we'll see other traffic where it'll go 420s constantly. So we can see that for sure. And sorry, the second part of the question was, can you say it again? What was the second part of the question? How do they report? Yeah, how do they report the data requirements? So there's a buffer status report. So it's it comes from the stations themselves, and it indicates to the access point the size of its transmit buffer, like what it's hanging on to and what it needs to send. And again, based on the buffer status report, the AP should be changing its RU allocation to kind of make sure that those buffers get drained, in a reasonable time. So we do watch that as well. That's some of the other things we're doing is looking at the buffer status reports and seeing how the buffer status report information tracks with RU allocation from the AP for the uplink traffic. So yeah, both good questions. Really interesting from the point of view of understanding how OFDMA is working. Again, our focus is on making that information accessible to people. We don't focus that much on trying to, kind of debug somebody's scheduler.
I would just add that we haven't seen more than 8 RUs allocated in an 80 megahertz channel.
Right.
And that's way below what is the maximum. What is the number of the maximum are usually?
37.
7, right? Even though we have connected 2 of our PAL boxes and we had 16 AIDs available, and we couldn't get more than 8 to be in an OFDMA frame simultaneously. So probably because it's still early technology, so that's one interesting observation so far. We have another question from Ravi. If we use multiple stay pals as synchrosniffers in the same channel, how do you handle the same frames seen from different sniffers? So,
well, we don't see the same frame, obviously, if they're, HE trig or MU packets, right? Those are only going to be seen by the one who he's focused on. But you're right, we will see, for example, trigger frames. The triggers will come to all of the stay pals, so the same trigger will be seen. I kind of talked about that a little bit at the beginning in talking about how we can use repeated packets to further time align the streams that we have. At the moment, we are putting all of the packets, even repeat packets, into the capture. But again, we do have the information. We can identify repeat packets, and we may, and this is something we work with our customers on. If that's important feedback, we could definitely weed out the repeated frames if that was necessary. So right now we don't. So we don't get repeated frames for HEMU or HE trig packets. We do get it for anything that's more like a control frame, like a trigger frame.
right. We decided not to be too smart and just let the user have all the packets for now, because in some cases they will also be at different levels, signal levels. Say if one sniffer probe is in one point in the mesh, the other is two nodes away through a repeater. They may hear the same packets, maybe not at the same RSSI. So for now, we're just leaving it as extra information. They're easy to identify, though.
Radha, how are we doing? Are you ready to switch back?
I'm just gonna run the test again. Give me a second. I think we're ready. My test has just started, so this test is actually setting up all the devices for the test bed. It's completely automated. It's gonna set up the devices and set up the attenuators and associate the client to the 5 gigahertz access point, and then it's gonna roam. So this is pushing the configuration from our UI, and we have our traffic pairs entered here. We're running traffic from our server to the client, and we can add all the attenuators here. So while this is just pushing the configuration, it's going to take a couple of seconds.
Yeah, while this is happening, I guess it wasn't really the focus of this seminar, but we can use it just to highlight something, which is that all the devices in our test bed exposed REST APIs. So they are fully automatable. And we have a set of, we have a Python library that lets you control all the devices, via Python. So we often will do complicated tests like this using automation, and you're seeing that happening live right now. Go ahead, Radha.
Yep. So I have the sniffer up again, and my test has started. So I'm just gonna show you the test running. And the client is first associated on 5 gigahertz. You can tell by the throughput and the RSSI is here. And as we are roaming, the RSSI is dropping, and I'm just going to put the sniffer capture right by the side. And we can notice the probe ID to see where the client is associated. So right now it's associated to the 5 gigahertz access point. The throughput is dropping, the RSSI is dropping, and that shows us the client is moving away from the 5 gigahertz AP. And now that it's disassociated, if we look at the sniffer capture, we see 2.4 and 5 gigahertz packets, and more of 2.4 because the client is seeing the 2.4 gigahertz AP. And once the RSSI is back, we see it's associated, and the throughput is back up. So client is on 2.4, and it's moving closer to the 2.4 access point. You see the throughput ramp up, the RSSI ramp up. And what the test also does is once it ramps up and to 2.4, we're going to ramp back and see the client roam from 2.4 gigahertz AP to the 5 gigahertz AP again. So at the same time, we can see with the RSSI changing, we see the data rate and the MCS drop and increase while it's moving closer, and we see the increase in throughput, we see the data rate increase. So now it's at the peak, and the RSSI is dropping again. So it's the client is moving away from the 2.4 gigahertz AP, and we can again see the drop in data rate, MCS, and the throughput simultaneously on the same plot. Since the sniffer capture is all synchronized in time, the roam time can be calculated using the sniffer captures or the UI plots. It's a with multiple and also the CSV reports, so we can find the roam time using 3 different. So now we see the RSSI is dropped down, the client is disassociated. And we'll see the sniffer packets go from 2.4, and we'll see some 5 gigahertz packets. And the client is going to roam back to 5 gigahertz. There we
There it goes.
The RSSI is improving, and it's going to go up in throughput and reach up to 800.
Okay.
All right.
We have a question, meanwhile,
Yeah.
from Feng. Can you explain, is it normal to see throughput drop for about 30 seconds?
Oh,
Or
the
close to
dropout
zero
time?
during the transition for about 30 seconds. I think that's known as a sticky client.
Yeah.
It's been with Wi-Fi ever since Wi-Fi was born. And we keep waiting for it to be fixed. And we think 11 KRV is the answer. And these drivers are also becoming mature, but they're not prevalent just yet.
Right. I think we actually configured this one to hang out. I think the roam threshold is quite low, so it's done this way on purpose for this demo. But as Fanny said, there are definitely Wi-Fi technologies that would speed this up if supported on both ends of the link. Okay, so let me wrap up here just real quickly. We'll certainly stick around for questions if there are more. But just kind of in summary, sniffing becomes more complicated as we have more complicated things to test. So either complex topologies like mesh and extenders, or advanced protocols like OFDMA. And for reasons that hopefully we've made clear today, those require some fairly sophisticated sniffing technologies. So our SynchroSniffer was actually invented really to address the topology issue, but it's also proving to be really indispensable for OFDMA sniffing as well. So that concludes the tutorial. So again, thanks for listening. If you remember kind of at the beginning of this, when I showed the large chamber, I talked a little bit about, path loss and link budget, and we thought it might be interesting to go over that in a little bit more detail in our next seminar. So if you would like to, please join us for that one. We're calling it Wireless RF Testbed Path Loss Analysis, and we'll go through all this stuff shown over here on the right. In addition, all of these seminars have been archived. So the first three, I think all the information is on our website, but the first three are at the links shown here, and this one will be archived as well.
Great. Well, with no more questions, thank you, folks, for joining us, and we hope you join us for the next one as well. Bye-bye, everyone.